Problem number 17. As shown in the figure, a ping pong ball with a mass m, with the initial horizontal velocity v and the angular velocity omega, comes into contact with the ground. Friction is not negligible, so both the velocity and the angular velocity of the ping pong ball changes. What is the critical velocity Vc such that the ping pong will stop and remain stopped? Treat the ping pong ball as a hollow sphere. Solution for problem number 17. Here we can use angular momentum conservation. If we take axis of rotation right in a table perpendicular to this picture, we can count what is the total torque of all forces around this axis. We have gravity force and we have normal force, which cancel each other. And also we have force of friction, which is going through this axis of rotation. So it means that the total torque acting on this ball is 0. It means that total angular momentum around such axis is 0. And let's write this equation for total angular momentum. If we have a solid body which is moving around axis of rotation, total angular momentum equal mass multiplied by velocity of this body and multiplied by distance from the center of mass to this axis of rotation. And we need to add here angular momentum around the center of mass. In our case, because omega is counterclockwise, that will be negative, and that will be negative I omega, and the total equals 0, because finally it will stop. From this equation we can count. Because I equal 2/3 mr square, we can insert this I in this equation and finally find that velocity equal 2/3 r omega, which is answer A. That was a solution for problem number 17. Problem number 18. A spinning object begins from rest and accelerates to an angular velocity of omega equal pi over 15 radians per second, with an angular acceleration of alpha equal pi over 75 radians per second square. It remains spinning at that constant angular velocity and then stops with an angular acceleration of the same magnitude as it previously accelerated. The object made a total of 3 complete rotations during the entire motion. How much time did the motion take? Solution for problem 18. First of all, we can find what is time for acceleration and deceleration. This we can count from formula omega equal alpha t1. So we have t1 equal omega over alpha, which is 5 seconds. After that we can count what is total rotation for this object. Total angle theta, which is 6 pi in radians. That's equal twice distance with acceleration, which is alpha t1 square, plus omega t2, where t2 is time for constant angular velocity. So from here we can find that omega t2 equals 6 pi minus 1/3 pi, which is 17 over 3 pi. And from here we can find that t2 equal 85 seconds. And total time t equal twice t1 plus t2, which is 95 seconds. That's the answer E. This is solution for problem number 18. Problem number 19. A semicircular wire of radius r is oriented vertically. A small bead is released from rest at the top of the wire. It slides without friction under the influence of gravity to the bottom, where it then lifts the wire horizontally and falls a distance h to the ground. The bead lands a horizontal distance d away from where it was launched. Which of the following is a correct graph of RH against d square? Solution for problem number 19. First, we can find what is the speed of this bead when it leaves this wire. From energy conservation, we have v square equal 4gr. Now we know what is speed, and we can count what is total time to travel. For that, we can use formula h equal 1/2 gt square. From here we can find that time equal square root from 2h over g. It means that total distance equal vt or square root from 8rh. And finally we have rh equal 1 over 8 d square. This is the graph D. That's a straight line with the origin in a 0, point. D is correct answer. That's the answer for problem 19.